Let us now address the question of the expanding universe and what does it really mean. This is usually something that baffles many people when they first hear about expanding universe. What is it expanding into and how? The important notion here is that there really are two different kinds of coordinates in general relativistic cosmology. There are the co-moving coordinates, which expand as the universe expands. Examples of those would be unbound systems, like any two distant galaxies that are not gravitationally bound together, or wavelengths of massless quanta, like photons. But they're expanding relative to what? There has to be a fixed set of coordinates, and those are called proper coordinates. This is what you usually think of as coordinates, which are fixed, and space expands relative to them. If it wasn't the case, we couldn't tell that there was an expansion because everything would be expanding. Well, things that do not expand with expanding space are atoms or molecules or solid bodies like planets, or in fact any gravitationally bound systems like the solar system, stars, and galaxies. So galaxies don't puff up with the expanding universe. They stay the same size, but they do go apart. Okay, so what's the universe expanding into? Well, it's expanding into itself. There is nothing outside of it, except for a purely hypothetical multiverse, but the same would apply in each one of its constituent bubble universes. Consider a positive curvature universe. That's like the surface of a sphere, except in one extra dimension. It has finite volume and finite surface, but it can grow. So there is no edge, and it can expand. If you will, the fourth dimension into which it's expanding is time. Now, a flat or negative curvature universe is simply infinite in all directions. And you can think of the grid stretching out everywhere. So in either case, there is no edge, and there is no center because of homogeneity and isotropy. So the universe is expanding into itself, in a sense, and there is nothing outside of the universe. How does it expand? The function that describes that is called the scale factor, which we mentioned earlier as a function inside the Robertson-Walker metric, usually called R of t or A of t. If you take any two distant points and measure how their distance changes in time, that's essentially what scale factor is. And because the universe is homogeneous and isotropic, exact same function will apply to all points in space and time. So if we knew what that function was, then we can tell exactly how the universe is going to evolve. Being able to do this is essentially what cosmological models are. And we do this by solving the Friedmann equation, which is what Einstein equations reduce to after assuming homogeneity and isotropy. But first, let's think about cosmological redshift. This is the usual balloon analogy. Inflate the balloon and points on it go further apart. Well, if you glued little buttons on the surface of the balloon, buttons would not be expanding as balloon expands. Those would be like galaxies. But if you drew wiggle lines on the balloon, those will stretch as the balloon expands. Those will be like photons. So we talk about the redshift since the wavelength tends to increase, moves to the red. And familiar notion is the Doppler shift, which in non-relativistic case is just the ratio of speed by which something is moving to the speed of light, or speed of sound in the case of sound Doppler shift. In special relativity, there is a little bit of a relativistic correction shown here. So we do think of cosmological redshift often as being a Doppler shift. Galaxies are moving far away from us, therefore there is a Doppler shift in wavelength stretching. But really, more correct explanation or more correct way of thinking of it is that it corresponds to the stretching of space. Well, if any distance stretches according to the scale factor R of t, then the wavelengths will do the same. And our definition of redshift is change in wavelength divided by wavelength itself. And so if we divide these two, we get that the scale factor, ratio between scale factor now and some different time, is 1 plus redshift. So we essentially use 1 plus redshift as the measure of cosmic expansion. This turns out to be exactly equivalent to the Doppler shift explanation, but this is probably a better way of thinking about it. Consider an observer at a radius of 0 and some radial light rays, and since they move at null geodesics, that means that sum of the spatial displacement is equal to temporal displacement, and the following equation must apply according to Robertson-Walker metric. So if we emit a ray of light at time t1 and it's observed to the t of 0, then integral over those two paths has to match, and according to this formula. So if a co-moving source is some distance r and its coordinate is fixed, well then the relative displacements or relative increments in time scaled by the scale factor must be the same. So therefore, there's going to be a redshift in expanding universe. You can divide the two, and it's the exact same result as we got before. Well, let's consider Hubble's law in the light of this explanation. For a nearby source, we can write this as the following expression. R dot is the time derivative of scale factor at this time. So the redshift is essentially time derivative of the scale factor divided by the local scale factor itself. In other words, it is a dimensionless fractional change in scale factor, and that is what Hubble constant is. So we can derive Hubble's law directly from Robertson-Walker metric, and Hubble constant is not really a constant. It changes in time, but at any given time it is a constant, obviously, and so it's an instantaneous expansion rate. Today's value is usually denoted as h naught, a little zero subscript. Well, finally, here is something interesting to think about. The holy cow of physics, conservation of energy. Well, it turns out energy is not conserved in an expanding or contracting universe. There are a couple simple examples. Those photons that stretch with redshift, where does their energy go? A photon may be emitted, able to ionize a hydrogen atom, say, but when it's received, its energy is much less because wavelength is stretched. Where did that energy go? Or the other way around, take two galaxies. They're not gravitationally bound, but they still have some potential energy relative to each other. Expansion of the universe carries them apart. The potential energy drops, so the system has gained energy. From where? So the upshot is that energy is actually not conserved in an expanding universe. It's something to think about. So next time we will talk about Friedmann equation, which is the actual way in which we compute cosmological models.